the structure of final examination, that is equal to that of midterm exam. First one, the default question is about your investment idea. So propose your investment idea with convincing logic to support it, and then validate the idea with complete data analysis. In the midterm exam, it was preliminary data analysis, but now you have to do complete data analysis. And in addition to that, now I impose a format, okay, to your final exam. So your final exam should follow this format, okay? You link, you click the link, and then there is the information how to write your term paper. There are basically two ways to write your term paper. Okay. Actually, first, let's read from first. So, use the paper in the following link as a template. So, in the link, there is a MS Word document. So, please download MS Word document and overwrite on it. Then there will be no font or line spacing problem. Okay. So grading, of course, the function of interesting topic, interesting analysis, clear writing style, and the format structure. Format and structure is the most important factor in grade. Okay, it sounds strange. So rather than content, format is more important. Okay, so then let's discuss what format means. There are two ways to write a term paper. First one is inductive. Second one is a deductive way. Inductive method will follow like this. So there should be of course title. Okay. Any investment idea or any case study or any write-up relevant to this class will be fine. And after title, there is the introduction. And the introduction is of course the first part of your paper. And the very first introduction should start with the first 5 sentences of your paper. This is the first 5 sentences of your paper. So the first 5 sentences will be first paragraph, the very first paragraph of your term paper. So your first paragraph is either 5 or 6 sentences. First sentence is optional. So it should start with an example related to your investment idea. So basically you want to get the attention of the readers through a tangible example. Okay. Second one is basically discussion of the topic. So you basically have to say why your research idea, why your investment idea is interesting, why it is important. In the second sentence. Sentence number 3 is existing literature on the topic. So basically you have to go through relevant literature. You should check relevant literature in Google Scholar, for example. And then there will be many papers related with your investment idea. What you have to do is basically you don't have to read everything. You read maybe most cited 3 or 4 papers, quickly go through it and write down the consensus. Okay, consensus of existing literature in one sentence. Okay, that's the consensus. Sentence number 3, and sentence number 4 is example of existing literature. So sentence number 3, you write down the consensus of existing literature, and sentence number 4, basically you explain, for example, who said something like that. So illustrate the consensus with specific citation. Sentence number 5, basically you want to say what's wrong with the existing literature. Okay? And then of course, given the limitation, now you propose your idea, propose your investment idea or research idea. Basically, given the literature question, given the consensus of existing literature, and given the limitation of existing literature, now you want to propose your own idea. Okay? 5 or 6 methods, it will be first paragraph. Okay. Now, the other part of the introduction is basically detailed explanation of the first 5 sentences. Explain briefly the concept of your paper. What is your research question subject, investment idea? Why is your research question is important? Why your investment idea is important? Is there any research similar to yours? And what are the limitations of the similar research? And what is the additional contribution of your investment idea to the previous research? This is the introduction. Now next one is case or data selection. Okay. Next step is you have to go through the data. So basically you can use both qualitative or quantitative data. Quantitative data maybe you can get from Google Finance or FM Guide or Naver Stock, whatever you want. Qualitative data is maybe news article, interview with other people, or other archive documents. So it doesn't matter. You can use both qualitative or quantitative data. But since it is econometrics class, I suggest you to use quantitative data. So you select data, okay? So you have to explain why is your case or data relevant to your research question or investment idea. Now explain why is your case important, why is your data important to those in academia and practice. Academia is like professors, practice is like managers, like Dr. Kao, okay, who did presentation just before. Okay, now you provide the logic, what data you need, and then next one is you have to describe it through what process you collected data. So this data collection, this section should be detailed. Okay, what data did you collect? Where did you obtain the data? How did you collect the data? About quantitative data, maybe standard database or survey. Qualitative data means interview, archival analysis, or media search. So describe in detail how did you collect data. Once you have data, then now you have to do the data analysis. Okay. So if it is a qualitative data, basically you want to write down history, background, and other information about your case in your family. If it is just data, you can put on the regression or whatever analysis you want to do. Okay. So basically, you want to find the relationship between the variables in your data. So basically, given the two interesting variables, you want to investigate how one variable change, when one variable changes, how the other variable changes. Okay. So once you did the data analysis, now you have to generalize your data analysis. Generalization means you have to develop a hypothesis or proposition. Okay. Through data analysis, okay. So from this data analysis, you should need a logic to proposition, and now you have to derive a proposition from the data analysis. So proposition should be like this: domo x, domo y. So x is cause, y is effect, cause and effect. For example, the taller a man is, the more popular he is. Tall man, height is the cause, popularity is the effect, something like that. The more inflation, the better gold performance. Okay, in that case, inflation cause, performance of the gold is the effect. Of course, given if you believe that proposition, if you find something through your data, if you find a hypothesis like the relationship between gold and inflation, then it can become investment idea. So basically, you are the your proposition will be your investment idea. Anyway, your proposition should be like domo x, domo y. And then you have to think how are your proposition relevant to your research question. It should be relevant to your investment idea. And then you have to find the similar proposition or theories in the literature, and you can discuss. There must be someone out there who says something similar to yours. And then you can compare your propositions with those in the literature. Okay. So from data analysis, you generalize and you develop proposition, and that becomes basically investment idea. And once you develop proposition, now you have to relate it back to the literature. Okay. Now you have something new. Okay. You have your own thought. Now it is time to compare your thought with literature. How does existing literature help you to generalize your proposition? And what paper has similar proposition to yours? What papers drive similar conclusions to yours? What are your additional contributions of your paper in detail? And which paper can highlight your contribution? Okay? Basically, you want to relate what you find with those other people already found. Okay? And next section of course conclusion. State what you have learned and limitation of your analysis. I understand your analysis or your term paper is basically not perfect. So you have to admit what is wrong with you, what is the limitation of your analysis, and maybe how future research can improve. So this is the inductive way of writing a term paper. So you start from data analysis, generalize, and it becomes your investment idea. Okay? So data, proposition, and idea. Another way is a deductive way. So it is 비납법, 면역법. Okay? In the deductive method is basically you start from theory. From theory, you generate investment idea, and you test those investment idea with data. So it is the opposite way. So deductive way, of course, you need a title and introduction. Again, even if it is deductive writing, still you have the same first 5 sentences. Still you have to write down first 5 sentences of your paper. Explain briefly the concept of your paper. What is your research question subject? Why is your question important? Is there any research similar to yours? And what is the additional contribution of your paper to the previous research? Then next you have to go to literature review. So you have the research question, right? Investment idea. Then you check the literature, whether people something similar to or opposite to your own idea. What papers have similar questions to yours? What papers drive similar results to yours? And what are your additional contributions in detail? And which paper can highlight your contribution? Now you have understanding. After literature review, maybe you have understanding about the literature. Then it is time to develop theory. Okay? Develop your own theory. Basically, it is generalization. You find, so you have to abstract. You have to, how can I say? You have to, so basically you did a study or you did literature and you should formulate your own idea and you have to state it. So what is your theory about the research question? So about research question, you did a similar research and now you have your own theory about research question. It doesn't have to be novel. It doesn't have to be new. Okay? And find the similar theories in the literature and discuss. And maybe you can compare your theory with those in the literature. Okay? So the theory part. And from this theory, okay, in the deductive method, you derive your proposition from theory. In the inductive method, you derive your proposition from data analysis. Okay, anyway, from theory, you develop your hypothesis or proposition. So logic from theory to hypothesis, you have to discuss that and derive a hypothesis from theory. Okay, and again, the hypothesis should be like the more and the more. Okay, again, from the literature review, you formulate theory. From the theory, you have hypothesis. Okay, you have a cause-and effect relation between X and Y, your hypothesis. Then it is time to test your hypothesis. Okay. To test your hypothesis, of course, you have to operationalize the concept X and Y. You have to determine how to measure and how to measure Y. Okay. If it is your hypothesis, the total man is the more popular he is, then you have to determine how to measure height of the man, how to measure popularity of the man. Okay. It would be easy, like centimeter, feet, inch, nothing like that. Popularity is trickier. Okay. It is like a number of follow after blind date, something like that, or survey. So you should be creative about this part. About the relation between inflation and gold price, then it wouldn't be difficult. Inflation is easy to measure. There is a lot of measures about inflation out there, like CPI. Performance of the gold, maybe you can check the commodity index. Anyway, the idea is basically you have to operationalize the X and Y. And then you want to measure X and Y, and then you have to get the data. And data source thinking. What data did you collect? Why are your data relevant and important to your research question? How did you collect the data? And quantitative data means standard data, and survey, qualitative data is again interview, archive, or another media search. Okay, then you have to do analysis. You have the data, you concept, now match X and Y. How Y changes and X changes. Okay. So it is done. Now you conclude. In conclusion, same. State what you learned. Discuss your own limitation. Okay. So it doesn't matter which way you write on paper. Both inductive or deductive methods are fine. Any question? So it is question number 1 of your final exam. Actually question number 0. Okay. Now question number 1 is write R code. Okay. Basically you have to check the Hurst book at chapter 12.4. Okay. Then there is formula for choose option, barrier option, and loopback option. There is duplication of this and this. So in the book there is formula. All you have to do is implement that formula through R. That shouldn't be difficult, right? You don't have to know what is the choose option, what is barrier option, what is loopback option. All you need is just a formula. And for this formula, actually you don't even need a Hurst book. If you do Google those concepts, you can find the formula for them very easily. And there is optional question, compound option. It is difficult. It is difficult, so it is optional. But if you do this homework, actually, if you solve this problem, you will get higher grade. Question number 2 is the same to midterm exam. Download events data about North and South Korea events, and then your midterm exam is actually your writing, your solution for the midterm exam is not entirely good. So I'll give you another chance. So please improve your analysis for final. Okay. So due date for this final exam is 6/15. Okay. Please submit your homework to this email address. Any question or any issue?
What if my data analysis is perfectly wrong? Yeah.
What do you mean by perfectly wrong?
After doing my data analysis, like a regression, however, the coefficients is almost 1.
If it is not significant,
Yeah.
then it is fine. Which means maybe your investment idea doesn't work. That is fine. If you find insignificant results, it's fine. Any other question? So you have 1 month, so good luck. So you mean you have to start final exam right now. Okay, that is the final exam, and there will be presentation, class presentation. Okay. Everyone should do the presentation about your investment idea next week, June 3rd. Okay. So for the presentation, I also have a format for your presentation. So if you to know the format of your presentation, you can click this 5-page presentation. 5-page PPT presentation. Okay. So basically, I want you to make 5 pages of PPT file. Okay, only 5 pages, and then you can spend 3 minutes per page. So it means you will have 15 minutes. Okay. So you should finish your presentation in 15 minutes. If it is over 15 minutes, then I will discount your grade every second it is over. So if you do the presentation in 16 minutes, although it is given 15 minutes, if you do it in 16 minutes, which means that you will lose your grade. But if you can finish your presentation in 10 minutes, that's fine. You don't lose anything. It is actually good. If you can finish your presentation in 10 minutes compactly, very well, that is actually better than 15 minutes. But you should avoid spending more than 15 minutes. That's very crucial. Okay. If presentation is over 20 minutes, then basically you will get 0 point from your presentation. Okay. Right. So if it is your presentation A, 1 minute later B, 1 minute later C, 4 minutes later D, 5 minutes later F. So 5-page presentation. For your presentation next week, there is again two ways of doing the presentation. Of course, it is deductive and inductive. Okay. So for PPT, if you click this and you can download a PPT slide, so you can just override it. It is like a McKinsey format. It is standard consulting format, so please use this. Please don't use like a fancy, like elegant presentation. Just use the simple McKinsey format. First, deductive one. Okay, deductive one. Page 1. Okay, PPT slide number 1. Research question, and you write down proposition. The more X, the more Y. Page 2. Logic to proposition. You have to explain how did you derive the proposition. Then it is theory based, so there is a theory or theoretical background, there is a key literature, and you basically write down how you derive proposition from those theories. Okay, so from research question, then theory, and then okay, your proposition. And then basically you have to test it. So data, what is your data? How did you collect the data? How did you define the concept X and Y in the data? So this is explanation. Page 3, slide 3 is about data. Slide number 4 is data analysis. Basically, you want to match variation in X and variation in Y. And explain does the data validate your hypothesis or not. Page 5, conclusion. Says what you have learned and limitation of your analysis. Okay. Actually, there is a sample of my former students. I think it is slightly different from. So yes, she didn't follow. So it's page 1, page 2, page 3, page 4, page 5. Oh, she spent more than 5 pages. But this is actually, I think during the class, she did play only 5 pages. But this slide is for academic conference. So she made more than 5 pages. Okay, so she was a student at OCW-HYU University, and her term paper and presentation was so good. So I recommend her to refine the writing, and we submit the paper to one of the best conference, domestic conference about strategy, and they accept the paper, and she did the presentation, and this is the presentation file for that academic conference. I remember she did a very good job. Yeah. So it is her proposition. So basically she did a deductive way of research. Anyway. So actually yeah, she did inductive one. Next one is inductive method. So page number 1 same. Research question and background literature. Slide number 2, you now have to select the K or data. How did you select K or data? What method did you use to collect data? Okay. Page slide number 3 is data analysis. You are to match the variation in one variable to the variable in another. Okay, culture and performance for example. And actually you can make this data analysis into the 2 slides. So if you do the inductive presentation, actually you can spend 1 more slide. You can use 6 slides. And within case analysis, investigate variation of the variable and investigate relationship between variation and variable. So from data analysis, basically from data analysis now you extract hypothesis, the more X, the more Y. Okay, conclusion is basically compare your results, conflicting results, compare your results with similar results, and what did you find? Basically, proposition becomes your investment idea. It should be relevant to your investment idea. Okay. Oh, by the way, about final exam, there is also sample. Final exam about first one. Again, I have a sample from my former students. Okay. Actually, I remember last year, Hanyang students also have very good. I found a couple of very good term paper last year, but actually I didn't update it. So since I have only sample term paper from EWA almost reverse. So let me see one of them. So it is one of the term paper. So they analyze key success factors that contribute to the Samsung's performance improvement in the world market based on Porter's value chain model. Okay. So it is not intended finance paper, but it is very good. So it was their term paper. Okay. Very nice format, very good value. Okay. Yeah, we will append it and then tables and figures. About 53 pages. So it is 53 pages, very good. It is a very good report, but you don't have to write this long paper. Actually, this long in it, you can spend like 100 paper, 100 pages of paper if you want, but it doesn't matter. Quantity doesn't matter, only quality matters. So if you can write very impressive one page of paper and address all the format guidelines in only one page, that will be fine. Okay? But I think it will be more challenging to write 100 pages paper. So anyway, it doesn't have to be long. There is no upper limit and lower limit for the length of your paper. Okay. So your presentation is due June 3rd. Sohei is not here, so please tell Sohei what she has to do. Okay. Any question? Still we are using a linear model, y equals x beta plus epsilon. So same specification. And then mean of epsilon is still 0. So mean of epsilon is 0. And then x and epsilon are still orthogonal to each other. So conditional on x, mean of epsilon is 0. Okay. And then x and epsilon is 0. And then previous specification such that epsilon prime is sigma squared and I. So basically error terms are not correlated with each other whenever we have different observations. And for each observation, the regression error is the same variance. Okay. So it was the assumption, and we want to relax assumption number 4. Okay. So in this section, we consider relaxing assumption 4. Okay, and instead we assume the specific value of epsilon prime is some sigma, some omega. Okay, t by since we have t number of observations, so our various covariance matrix of error term is t by t. Okay, where so omega is a symmetric, positive definite matrix. Okay, first, why it should be symmetric matrix? What is symmetric? Why should it be symmetric? It should be symmetric. Why? Cheer. Why? What is a symmetric matrix? Can I remember? What is symmetric matrix?
I cannot explain in what? It's like the calculator.
Okay. Okay, that's good. I mean, it is simple. If a transposure of a matrix is same to itself, it is symmetry matrix. Okay. Okay. So, Peckel one is similar. So, on the diagonal matrix, this side and this side are same. So, why it should be symmetric? Why? Yeah, why it should be symmetric? Yeah. So suppose so it is ith element of epsilon, jth element of epsilon. So for variance between the two, this put is ij, and then eji, right? And then basically this and this should be same, right? So therefore, omega should be symmetric. Okay. Next one, it should be positive definite matrix. Do you remember definition of a positive definite matrix? What is the positive definite matrix? Do you remember? Oh, maybe I think we skipped it. K of positive definite. 한J. What is the positive definite? So suppose C is T by 1 factor. Suppose C is T by 1 factor. And if, okay, so if we do this operation, then we will have is T1 by T, T by T, T by 1. So it will be a constant, right? And if this constant is greater than 0, okay, then it is a positive semi-definite. So for any, okay, for any real valued vector, for any vector, if we have this relationship, it is positive semi-definite. This omega matrix would be positive semi-definite. So why positive semi-definite? Okay, make it a likelihood function. Okay, the likelihood function. So given data x, the likelihood of y, probability density of y can be described like this. Okay. So it is like multivariate normal distribution. So to remind you, okay, probability distribution. Okay, so suppose x is, okay, what is the probability distribution of x? Do you remember? 현재, what is the probability distribution of x? Anyone remember? Okay. So fx, probability distribution of x, in this case it is okay. Do you remember this? You saw this before, right? In the earlier part of this class, you saw this. So it is a single value. Okay, it is x is scalar, it is a single value, and it is single value, and so it is scalar. It is scalar. But if we have vector, epsilon is mu, so mu is the vector, so omega is the vector. Right? Omega is now matrix. So it is T by 1 matrix. So T by 1 is T by T matrix. So in this case, it looks like the distribution function is more generalized than this, and it looks like this. And in this case, of course, mu of y, so it's probably distributed y given x. And since mean of y is simply x bar, okay, and standard various covariance matrix of y given x is simply omega, right? So we have this. And we want this part greater than 0. As this part is greater than 0. Likewise, we want this part, okay, we want this part greater than 0. So density does not explode. Actually, for more intuitive reason for omega, positive semi-definite step, consider a covariance matrix omega over a random vector epsilon with mean of epsilon 0 that is not positive semi-definite if there is some constant such that c prime omega c is less than or equal to 0. That is not positive semi-definite. Now consider the linear combination C epsilon, but C is the scalar, then value of C prime epsilon. Okay, so it is basically a linear combination of epsilon. The variance of C prime epsilon becomes less than or equal to 0. It is possible that some variable has negative variance. No, right? Variance cannot be non-positive. Variance should be greater than 0. Therefore, omega should be positive semi-definite. If it is not, there is a weird case such that variance of the random variable becomes negative or 0. Now consider a special case when t is 2. Okay, so we have two observations. Okay, so and omega looks like sigma 1 squared, sigma 2 squared, and the off-diagonal term is rho sigma 1, sigma 2. Okay. So in this case, of course, rho is the, since it is 2, right? So sigma 1 is the variance of the epsilon 1, sigma 2 squared is the variance of the epsilon 2, and they are the covariance of the first and second element of the epsilon. And we can decompose covariance into the correlation and standard deviation of the two. Right? So when t is 2, omega looks like this. It should be look like this. Okay. And this should be pi. And clearly it is symmetric, right? Since this and this are same, they are symmetric. Okay. And to be positive semi-definite, okay. Actually, there is an easier way, so it is a definition of positive semi-definite, and there are actually easier ways to test positive definiteness of the matrix. So in this case, it's 2 by 2 matrix. So the diagonal term should be positive, and then determinant of the matrix, its 행렬식 determinant of the matrix should be positive as well. Okay. If this condition and this condition holds, then 2 by 2 matrix is positive semi-definite. And this is obviously positive. Okay. And to make this one positive, okay, which means that we have to separate out sigma square and sigma square. So basically correlation should be less than 1. Okay. Correlation should be less than 1, then the matrix is positive semi-definite. And we all know correlation should be less than 1, right? Correlation cannot be greater than 1, right? So, under very reasonable condition, it is positive semi-definite. Could you please raise your hand if you take mathematical economics before? 수리경제학. No one took mathematical economics. You did? Okay. Oh, everyone took it. So you learned optimization, right? Did you run Hessian matrix? So if there are I think if you run mathematical economics and if you run optimization in the mathematical economics class, you must run positive semi-definite over there, no? So, I mean, didn't you run ordered Hessian and Hessian matrix to test whether a point is maximum or minimum on the constraint? No? That's the most important part of the mathematical economics. Okay. To get the maximum value or minimum value. Okay. Anyway, to check whether a matrix is positive semi-definite, okay, A equals A11, A12, A21, A22, something like this. And basically, let's call this one as a H. And we call FHI as the first I part. So this length is I, this length is I. So it is some matrix of the H. Let's call this one as I, HI. Okay. And a matrix is positive semi-definite if okay. So it is another way to define positive semi-definite. So this and this is equivalent. And in this case, we use this condition. So you never learned this one? I think you did. In Lagrangian, did you learn Lagrangian? Okay. If there is a restriction, okay, restriction in optimization, we will have Lagrangian. Right? In case of Lagrangian, we construct like a bordered Hessian over here. So B1, B2, 0, B1, B2. And then there is another condition for positive semi-definite or something like that under the border. That is very important actually. It is important not only econometrics, it is also important mathematics. So let me check. Positive definite. Positive definite matrix. In linear algebra. Positive definite matrix is a matrix that in many ways is analogous to positive real number. Okay? So positive semi-definite is similar to positive real number. A notion is closely related to the positive definite symmetric by I don't know what it means. Okay, it doesn't matter. Okay. The definition of a positive semi-definite matrix looks like this. Okay. This is exactly identical definition I told you. For matrix G. So G is a conjugate transpose of C. So since in this case C is the real number. So conjugate value, okay, conjugate value of the C is a safety set. If it includes a complex number, okay, under conjugate factor, it has a negative sign. Okay, you have to multiply negative minus number 1, okay, into every complex number. So anyway, every conjugate transpose of G, G prime and G should be positive. Okay. Then it is positive semi-definite. So this is a positive semi-definite for a vector with Z1, G2, so like this. So it is always greater than 0, so it is positive semi-definite. An example of a matrix that is not positive semi-definite, but is positive definite. Okay? Not positive, so this matrix is clearly not positive. It has negatives over here. But it is still positive definite because we're given x1, x3, x prime, m, x looks like this, and if we solve this one, then eventually it becomes like this. So it should be positive. And this one is not positive definite because for 1 minus 1 it is negative. Okay, then how to characterize positive semi-definite? 。 . 。  . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 。 . 。 。 . 。 。 。 。 。 。 。 。 。 。 。 。 . 。 。 。 。 。 。 . 。 . 。 。 . 。 . 。 . Okay. So all eigenvalues. So there are many ways to define positive, to characterize five. So they are all mathematically equivalent. So this is definition of positive semi-definite that if we multiply vector, same vector each side, it should be positive, right? Another one is for a matrix to be positive definite, all eigenvalue. Okay, you already know eigenvalue. Eigenvalue of matrices should be all positive. If all eigenvalue is positive, then a matrix is positive definitely. And I think there is a sesquilinear form divided inner product Cn. There is not important. Okay, that is the grand matrix, collection of linearly independent vector. Right, and it says so. Okay, this is the one. So if M, the upper left 1 by 1 corner of the M, upper left 2 by 2 corner of the M, so like this. Okay? And M is there. In other words, so all the following matrices have a positive determinant. If their 형용식 positive, they have 형용식 is positive, so this determinant is positive, then it is still positive semi-definite. Okay? And there is a unique lower triangular matrix M. Lower triangular matrix L means this part is some number, but this part is all zero. Okay? So low triangle part is non-zero. So if there is a unique lower triangular matrix L, such that we can decompose M into the L star. Okay? L has conjugate transpose of L, and since we deal with only real valued matrix, L is just a transpose of L. Okay, so if we can decompose M to L transpose, then it is positive semi-definite. Okay. And the quadratic form associated with M is regarded to be a convex function, and there's a global minima, and this is positive semi-definite matrix. Okay, and this is very popular, common in optimization, especially this characterization, especially very common in finance mean variance optimization actually. Okay, Wikipedia is very good. And then this is positive definite, and there is also notion of positive semi-definite. Positive semi-definite can be equal to 0. So if this linear combination, so this product is greater than equal to 0, then we call it positive semi-definite matrix. Good. Further properties. That is, I don't want to read this. Okay. Very good. Cholesky decomposition. As lower triangle. Okay? So if there is a unique Cholesky decomposition, then this is positive semi. Any question? Okay, so as far as the correlation is concerned, then a general matrix, general variance is positive semi-definite. Okay. Now let's talk about example like tightly used autocorrelation, heterogeneous elasticity, spatial correlation, and random effect model in parallel. Okay, first examples of covariance matrix. Now suppose y is x beta equals epsilon, same, and suppose epsilon t. Okay, so y is t by 1 matrix. So the small t is t element. So t element of epsilon is actually t minus 1 element epsilon multiplied by rho and some noise. Okay, some et. And suppose et is iid. Okay, independently, identically distributed with mean 0 and some constant sigma. Okay, suppose our error structure looks like this. Then let's analyze how our variance covariance matrix of epsilon look like. Then clearly, exponential of epsilon should be 0. Okay, and then second, epsilon square means looks like this, and this is square of this one. And if you calculate the square of this, then it looks like this. Okay. but they are IID, right? IID. So actually this one is still independent, so this part becomes 0. And expectation of this part equals to this part, okay? And expectation of this part becomes this part, right? Given the information, so we have, and we are interested in this part, right? And actually this one is also the variance of epsilon, so actually this variance of epsilon should be equal to rho square of this part epsilon and plus variance of this y knowledge. Therefore, we can solve this equation such that this variance of epsilon would be variance of this e y knowledge part over 1 minus rho square. Oh, by the way, this error is called y knowledge. This is very this is called one of the most basic time series model, also called the autocorrelated autoregressive model, and that is called, that part is called y knowledge. So basically, the variance of this epsilon is ratio between the variance of y knowledge and 1 minus rho square. Okay. Now let's calculate the covariance between epsilon t and epsilon t minus 1. Now, okay, from this relationship, we have this one, and this one we can solve it. So therefore, okay, we have this one. Basically, we know what is the variance of epsilon square. So basically, we want to plug this value over here, right? And this term is 0. So it is simply rho multiplied by this part. Okay, and epsilon t minus 2. Again, we have this one and we have this one. So it is epsilon covariance between t minus 1 and t minus 2, and we already know what the value of this part. And about this part, they are 0. They are not correlated. So expected value of this part is 0. And we already know this part, so it is just rho multiplied by this part. So we have rho square, variance of y knowledge, and 1 minus rho square. Okay? And if we keep doing this iteration, then covariance between epsilon and epsilon t minus k is basically looks like this. Okay? So basically we can characterize omega, and omega looks like this. Right? This kind of structure is called autoregressive order 1, or we call it AR1 model. Now this is MA model. Now let's suppose that epsilon is now linear combination of y knowledge. So that we have to distinguish this one. So in this case, we have epsilon t minus 1, right? And we have ET. Now we don't have an epsilon t minus 1. We have ET and ET minus 1. Okay? And ET is again y knowledge. In this case, epsilon square looks like this. And we calculate it, okay, then it looks like this. And then since they are, this part is 0, okay, expected value of this part is 0 because ET is independently distributed. So this part will be 0. So it is A square, some sigma E square and B square, sigma E square. So we can put out sigma E square, so sigma E square, A square, A square plus B square. Right? And now we want to know epsilon t minus 1. So we have this one, and we have overlap of this one and this one, and this one and this one, this one, 0, this one, 0, this one, 0. So we can take it upon only this part. And this part is AB, so sigma E square. And then if we do t minus 2, then there is no overlap. T minus 1, and this is t minus 2, t minus 3. And there is no overlap, so this has to become 0. For any k greater than 2, this is 0. So various covariance matrix in this case looks like this. And this structure of error covariance matrix, if a covariance matrix has this structure, it is called moving average of order 1, MA1 model. Now this model is interesting. So y is expressed plus epsilon, and now we have epsilon t and epsilon t minus 1 and epsilon t minus 2. So error term at 2 periods ago still affect today's error term. And then if we do this operation, epsilon e t square, then we have this relationship, and epsilon t minus 1, then we have this relationship. More specifically, expected value of epsilon t square is simply square of this term, and this is first square, and this is cross terms. And then if we collect same parts, then we will have 2 rho 1, rho 2, sigma 1 square, and epsilon, and 1 minus rho 1 square and rho 2 square. Okay? And for et t minus 1, we have, suppose this one is sigma 1 square, and then it should have rho 1 sigma 2 square and sigma 2 sigma 1 square. Okay? And we have 2 equations, and we have 2 unknowns, sigma 0 square and sigma 1 square. 2 equations, 2 unknowns. So we can basically solve these 2 equations. Okay? We can solve these 2 equations, and we can get sigma 0 square and sigma 1 square. Equation 2 and 3 are 2 equations in 2 unknowns, sigma 1 square and sigma 1 square. And these are called Euler-Walker equations, although usually written in a slightly different way, and can be solved for sigma 0 square and sigma 1 square. Once we know sigma 0 square and sigma 1 square, we can solve iteratively for other auto-covariance terms, such as et minus k, suppose it is sigma k square, then it basically looks like this, and rho 1, sigma k minus 1 square, and sigma 2, rho 2, sigma k minus 2 square. But since we know 0, sigma 0, and sigma 1, right? So for the value greater than 2, we can use this value and we can solve iteratively. Okay. Anyway, this structure is called autoregressive of order 2. Okay. Then what would we mean by an ARP process? What's your guess? What would be ARP process? Okay. So this is AR2 process, right? So ARP process means that we have rho 1, epsilon t minus 1, rho 2, epsilon t minus 2, and rho 3, epsilon t minus 3, and we have this until rho k, epsilon t minus k. Right? Actually, rho p, epsilon t minus k. Then we will have an ARP process. And now suppose it is MA2 process. So again, we have similar, we have epsilon error term, and it is a linear combination of 3 white nodes. White nodes past 2 periods, or past 2 periods. And we can get the square and looks like this. And we can get the covariance between epsilon t and epsilon t minus 1. We can solve this, and we have this equation. And if we calculate epsilon t minus 2, and we have this. And for all the k greater than 3, we will have 0. Okay. And this structure is called moving average of order 2. What would we mean by moving average of order k? It is straightforward. It is t, so moving average up to order k. Q means we will have some term et minus q. Okay. Any question until now? Okay. And more general, where is AR? Okay, more general, suppose y equals x beta plus epsilon, and et, epsilon t, can be characterized this way. We have p number of history for epsilon, and we have q number of history of a white noise. And all white noise are IID, then we call this structure as autoregressive moving average of order PQ. And if you learn times it, I think even in R, there is a package to calculate this. So it is not difficult to estimate parameters for R mark, okay, peak model. Okay. AR animation, R mark, peak model. These figures are maybe proportional to this X independent value. So for example, if the sigma, if we have a model which is consumption and income, right? If we have more and more income, the volatility of consumption may be greater. So in this case, reasonably we can think that variance of the consumption will be increasing function of the consumption. Okay. So increasing function of the income or balance, which is actually permanent income hypothesis. If you learn macroeconomics. Okay. So another possibility is to suppose that we have now IT. So I is IT, I is maybe form I and T is maybe time. So it is maybe the stock I, maybe it's return from stock I at time T, something like that. So this kind of structure is a panel data. Panel data means that we have observation for a given time, for many observations for a given time, and we have multiple time. Maybe for the panel data. And in finance, we deal around with this kind of panel data. Okay. And if this has two structure, two errors, UI and epsilon IT, and UIT may vary only across I. So it is error only on I and independent of time, and epsilon IT is sharp to form I, maybe at time T, something like that. In this kind of structure is called random effect model. This is random effect model in penguin. Okay, what do the UI errors represent? So it is if it is a Y, we can regard Y as a form I return at time T, then obviously UI is a shock to the form all history, all time, and it's a specific shock for specific form. Okay, any question until now? Okay, so therefore, this kind of generalized error structure, omega, can happen because of the many reasons. And now next question is, when the error term, expected value of epsilon prime is like omega, then our question is how to estimate that. Okay. Suppose, let's go back to our OLS estimator, and OLS estimator looks like this. Okay. And suppose error term, so basically, we suppose error terms have like general structure like omega, and suppose we still apply OLS estimation, and let's investigate what happens. So again, consider OLS estimator. So beta is x prime, x inverse x prime y. And y is x beta plus epsilon, so the can be decomposed as this. So if we compute expected value of the beta hat, expected value of our estimate, then it is still better, okay? Because x prime epsilon is 0, right? So it means that more general covariance matrix structure has basically no effect on the unbiased estimate of OLS. So even if an error term has very general structure like omega, and if we still use OLS estimation, still we have basically unbiased estimate. But the problem happens on the variance of the variance covariance matrix of our estimate. Okay. However, so let's calculate the variance covariance matrix of beta. So variance covariance of beta has basically is constant, so it is determined in this part. So this one multiplied by transpose of this one, so it looks like this. And then they are all we regard constant, so we put expected value in the middle. Okay, and epsilon prime is, we know this part is omega. Okay, so this one looks like this. In our OLS estimator, okay, OLS estimator, variance covariance matrix of our beta looks like this. Now it is different. Actually, it is easy to say this is greater than this. Actually not great. And thus generalized covariance structure affect the covariance matrix of the beta head and thus inferences. Therefore it affects the inferences. We can correct the inference problem by adjusting formula. For example, suppose our hypothesis is the A beta equals C. Okay. Suppose this is our null hypothesis, and suppose it's our alternative hypothesis. This is not equal to C. And given this null hypothesis, okay, then given this null hypothesis, okay, given this null hypothesis, A beta head minus C, given the null hypothesis, it should equal to 0, right? And about this covariance matrix, so basically, okay, since beta covariance matrix looks like this, so we multiply A and A time here and here, right? So we have this structure. So various covariance matrix of A beta head looks like this. Okay. Therefore, since it is various covariance matrix, if we pre-multiply this term into the inverse matrix of the various covariance matrix and divide it with the number of restriction, which is k, then this one will have F distribution. So by checking this entire F distribution, okay, then you can test whether this null hypothesis holds or not. Okay. So it's a slight generalization from what we already learned. Now, there is still efficient issue. Maybe there is smarter idea to estimate better. Smarter idea than OLS, maybe, to estimate better. And the smarter idea is actually generalized risk curve. So suppose there is still an efficiency issue and we can do better than OLS, and reg H prime H is some omega inverse. And with H having a full length, one usual method is to do Kolaski decomposition. We already saw. So anyway, suppose you can find some matrix H such that H prime H looks like this. Okay. Then there is a continuous, actually there are a lot of matrices. If omega is positive slightly, and there are a lot of ways to construct this kind of matrix. This is not difficult. And anyway, using this, we pre-multiply H, then we have HY and HX beta and HX, right? And maybe we can define H as a like dy1 and HX like x1, and this is new matrix. So basically, we transform our data. Well, we transform our data y and x by pre-multiplying H. Okay. On the given structure, and now let's run the regression. Okay, if we run the regression, then beta head will look like this, okay, and they look like this, and they look like this. Okay. Given the assumption that H prime and H is omega. Okay. So this kind of estimation is called the GLS estimate. The only difference between OLS and GLS, generalized risk estimate, is about this two. We have omega inverse in this here and here. Okay. And about properties of GLS, so beta head looks like this, and y is simply x beta plus epsilon, and we put this, and then this one looks like this, and this part and this part cancel out, so we have only this part, beta plus this part. And if we calculate expected value of beta head, and this is constant, we have expected value over here, and we put expectation inside of this one, so we have this one, and this is 0, so it's the entire term is 0. So expected value of beta head is still better. So our GLS estimator is still unbiased estimator. Okay. Now next we want to calculate variance covariance matrix of the beta head. Okay. So it is basically beta head minus beta and beta head minus beta head of test approach. And then we know what is beta head minus beta. Beta head from this one, beta head minus beta is simply this term. Okay. Simply this term. So we have this and inverse prime and this. And we can put expectation inside, and we have this. And we know expected value of epsilon prime is omega. Right? So we have omega and they cancel out. if they cancel out and this cancels out. So we have only this part. Okay. And knows that this is the 0 and it is obvious. And which satisfies condition for OLS as well. And Gauss-Markov theorem says that OLS is blue when this is, and GLS is blue in general. Okay. Which means that GLS estimator is best linear unbiased estimator. Which means that GLS estimate is the most efficient estimator. Which means that the variance covariance matrix of this one, to compare variance covariance matrix for this one and this one. This one, actually this one is gray. So you mean I will not show mathematically. I will show mathematically, but variance covariance of matrix over this term. Okay, simply this is variance covariance matrix over beta on the OLS regression, right? And this is the so to compare OLS, okay, we have this, and the difference between this and this is actually positive actually positive definite matrix. Okay. So when we say, when we substitute this one, and it becomes positive definite matrix, and positive definite is similar to some kind of positive number or real number. So we can, I mean, it is not vigorous, but we can say this is kind of greater than 0. Okay, so this part is actually smaller than this part in matrix term. Okay, so in that case, you can say this variance is low, and since we have estimate whose variance is lower, then we can say it is more efficient. We say it is more efficient estimate. So basically, the conclusion is that, so basically it's comparison between GLS estimator and OLS estimator. And basically you can say more general argument. For any linear estimator, okay, about beta, is actually greater than, its variance is greater than GLS estimator. Which means that GLS estimator is most efficient in the class of linear estimator. In that sense, our GLS estimator is the best. Okay? So it is the best linear, unbiased estimator. We already shown GLS estimator is unbiased. So we call this GLS blue. And actually, it's the OLS is a special case of GLS on the homoscedasticity. Okay, any question until now? No problem. Okay, any question? GS is slightly different. You have another experience around there. Any problem? You can do homework if I give you. You can still do homework if I give you homework. No. So where is the problem? Please describe it. I am willing to explain it, okay? Anyway, in the GLS estimator, eventually all you have to remember is simply this one, okay, this one, this variance covariance matrix of the beta, and basically this one, GLS estimator. Oh, by the way, this one, this GLS estimator looks straightforward. But actually, when you implement GLS estimator with this matrix notation, it is actually not easy. Okay, this is not easy because this omega matrix is usually huge, so it is T by T matrix. T is the number of data, right? So basically, it requires getting inverse matrix of T by T matrix. It is huge. So usually, I don't think R can do it. Usually, it breaks down. So there should be a smarter routine to calculate this. Okay, now let's go to the next topic. Specifying omega in parsimoniously. Okay, in general, omega is not known. Okay? So we must estimate omega. Okay, and maybe we would want to test some characteristics of it. Okay? But in general, omega has a t plus 1 by 2 of independent, because it is symmetric. Okay, it is symmetric. So we have t plus 1 divided by 2 independent of element. Why? So it is symmetric, right? It is symmetric, and we have 1, 2, 3, and we have to add 1 up to the n of the t. So, and there are only t number of observations in our data. We have t number of observations, but if we take into account various covariance matrix omega, we have t plus 1 divided 2 unknown. So we have basically too many unknown elements to estimate without. So basically, we have only t number of observations, and we have too many unknowns. So without imposing some restriction on the omega matrix, basically we cannot estimate omega. Okay. So consider each of the examples below. So in this case, AR1 process. Okay, even though omega has t plus 1 divided 2, we have then number of parameters to estimate. But since this error term is this iterative structure, so if we know this omega and then this one, basically we can generate this whole omega matrix. Right? We already saw it. So basically, if we know this and this, then we can construct omega matrix, which looks like this. Okay. So if you know only two parameters, then basically we can construct this one. About MA1 matrix is still similar. Okay. In this case, this omega is 3 independent matrices, independent elements. This one and this one and this one. Okay, if we know this one and this one and this one, we can recover this AR2 process. MA1 process, we have unknown of this one and this one and this one. So again, 3 independent elements. About MA2, we have this one and this one, and a variance of white noise with 3 independent element. About armor PQ model, we have this one. So this omega will include P plus Q plus 2 independent element, like that. Okay. About heteroscedastic 1, then sigma has a T independent element. Indicate still we have too many independent elements. So indicate because we have only T number of observations. So basically we have to impose some restriction about this one. One way is looks like this. So suppose this one is all proportional to this one. And suppose omega is one independent element, the proportionality factor. Okay. So in this case, we model like a sigma t square as some constant multiplied by x squared. Something like that. Okay. Then it's one independent element, which is the proportional factor. Okay. Now about random effect, basically it has only two independent elements. About variance of this form level shock, and another shock which is form level and at a specific time. Shocks of form at specific time. So in each of these cases, instead of trying to estimate t plus 1 divided by 2 independent elements, we estimate only the number of independent parameters, and then we can construct this omega matrix. And next, estimating and testing for serial correlation. First, Cochrane-Oka procedure. So suppose, okay, consider y is epsilon plus epsilon, and again, let's say epsilon is AR1, autoregulated on 1 plus x. Okay, and our goal is to estimate rho. Okay, again, AR1 plus s looks like this. Okay, so this is AR1, and we want to estimate this. So the procedure is very simple. First we run regression. Okay, if you run regression, and then we collect residual. Okay, and if we write metric, and our regression error looks like this. And with OLS beta is unbiased estimate, right? Unbiased and actually is consistent estimate. So it means that these error terms are also unbiased and consistent estimate for error. So again, if we correct error, then simply we calculate this one. So basically, it's correlation, right? Correlation between two periods, covariance between the periods. So basically, rho can be this correlation. So rho can be the ratio between the epsilon hat, this error square, and this one. Right? And if we have this one and then divided by t, then we have what the standard deviation of white noise. So basically, based on these two, we can estimate parameters in A or O process about this one, and this one. Upon the U work, upon the Cochrane-Oka procedure. Okay, this is doable, right? So why don't you do the homework? So this is the next week's homework. So please use the data you already multiplied. Okay? So homework is homework due next week. Okay, so basically you did the regression of your stock return over pharma-fragility factors, right? You already did. And from that regression, you correct the error term. And using the error term, undefined factors. You change the message. Good. Okay. So pharma-fragility regression, basically you can correct errors and simply calculate those ratio, and that is your estimate of the AR1 parameter. And about various white noise, you have this one. T is number of observations in your pharma-fragility regression. So it is very easy to do. And about large sample properties, so probability limit of sigma square. So row hat, looks like this, and divided this one by t respectively. And this one probability limit can be separated. And this one is basically covariance between the two, right? So it looks like this. And this one common to variance by probability. So we know probability limit of this one will come to low. So it is consistent estimate. Since it is consistent estimate, this one is constant estimate. Okay. Actually about this part. Okay. So this is consistent estimate as well. Okay. And then compute. Next one is you can compute this whole thing. Okay. Then you step because they are all consistent estimator. So this omega hat will go omega. And next step is to do GLS about this part. You don't have to do this part. Okay? You don't have to do this because this material is too large, so it is not difficult to calculate. So please do the procedure only up to this part. Okay? Only up to this part. Just calculate this and this. Okay, don't do this one. Okay, so anyway, you can do GS, you will try to present this. And if we can do, so basically, another people do just only one regression. So in this case, we do the OLS, and from OLS, we correct the errors, and from the errors, and we correct this and this, and we can correct this one. But actually, some people go one step further. We know GLS estimated this one. From this GLS estimator, we can correct the error term again. And from the new error term, we can correct it, go to the step 3. We can maybe calculate this one and this one again. And we can go to this step again. Some people did again. And this is called, this procedure is called feasible GLS for the AR of the case. But people rarely do this feasible GLS. Although some people found that this is actually better than doing this iteration is actually better than just one-time iteration. And then Durbin-Watson statistic, actually this is important. So I want you to the Durbin-Watson statistic. Homework. Okay, so once you calculate, once you compute low, so okay. So Durbin-Watson statistic is simply you still use regression from OLS. So you have regression error, and you can calculate this one and calculate this. And Durbin-Watson statistics, which assuming that example AR1 process, because then Durbin-Watson statistic, which is ratio of this one and this one, and divided by 2, then this converts to sigma square, this converts to covariance, and this converts to sigma square, sigma e square. So basically Durbin-Watson statistics become this one, and they cancel out. And in limit, okay, Durbin-Watson statistic in probability limit converts to 1 minus rho. Therefore, we can do the test. So if rho is 1, which means that there is no AR1 structure in our error term, then our Durbin-Watson statistic should be 2, right? It should be 2. If our error term, our correlation between error, okay, AR1 term is positive, then it is positive. So Durbin-Watson statistic should be less than 2. If there is a negative correlation, it is negative, so W naught sensitivity should be greater than 2, right? The range of W naught sensitivity, given that rho is from 0 to 1, is correlated, right? So it is between 0 to 1. So it means that W naught sensitivity is between 0 and 4. Okay? When rho is 1, it is 0. When rho is minus 1, it is 4, right? So if you are interested in testing null hypothesis H, if rho is 0 and it is 0, then we can compare the W naught sensitivity to 2. Okay. However, in order to turn this into proper test, we need to know the critical value of W naught distribution, and then most econometric textbook has W Watson table. And I think in R there is also W Watson table. Okay. So let me check. So R Darwin Watson test. Okay. R Darwin Watson test. Okay. DW test. So DW test formula and then perform the W Watson test for autocomplete order by where is the example? Oh, DW test. I need to on the table. Linear one. Oh, this is convenient. We can use the entire linear object like regression. So basically, Darwin was Ln, and this is SL term, and we have final frequency factor. Darwin was what I know to know. So actually in R, it is very easy to do turbulence test. Okay, you don't even have to compute the regression error. If you plug just the equation into the DW test function, then it automatically generates all the values. But actually, I want you to do the whole work in the harder way. Okay, and then into R, we can use this. So there is a Darwin-Watson statistic table. Darwin-Watson table. Okay, so this is number of n, so this is number of data. So I presume that you have data more than greater than maybe 100. Okay, so it is number of data, and Darwin-Watson low limit and upper limit. So in this, suppose you have data 40 number of observations. Suppose you have x variable excluding intercept. Okay, so if we use power of 23 factors, then we have three. Okay, three number of variables. And suppose we have data of 40, and we can use this one, three number of variables, and we have 40. So 1.43. So if you want to do 95% interval, basically you have to use this one. Okay. So if your Darwin-Watson statistic is less than 1.34 or greater than 1.66, you have to reject your null hypothesis that Darwin-Watson statistic is 0. No, rho is 0. Am I right? This one, no, I don't think this is right. Darwin-Watson critical value. So this one X. I think this one is actually better. So we have three factors. So we have to use this, right? And suppose we have like 40 number of data. 40 number of data. So we have to see. Then it is. Okay, this is Darwin-Watson statistic, and then K13, 14. Okay, this is Darwin-Watson statistic, 1% significant point. So suppose we have three factors, and suppose we have observation like 17. Okay, then upper and lower bound is 1. Okay, so our Darwin-Watson statistic is greater less than this one or greater than this one. Then we have to reject our null hypothesis that rho is 0. Okay. And if we want to use 95% error, then we have to 95%. Okay. Table 2, table 1. Okay, so this is 95% and yeah, this is 99%. So if you want to do 95% test, and suppose we use three factors, and we use 17 data, then low bound is this and upper bound is this one. So if our estimated low is between this value, then we cannot reject null hypothesis. If it is outside of this range, then we have to reject null hypothesis. We reject null hypothesis. Okay, so this is the homework. And of course, easier way to do the homework is to use default function. Okay, default Darwin-Watson test function already in there are, which is DW test. And in DW test, actually, if you put pharmacokinetic factor model, write down your model inside of the function, then you can do all these tests directly. Okay, good. Any question until now? Okay, no. So Darwin-Watson statistic is easy. Now estimating log omega in general, and in general assuming that we have specified omega in terms of a small number of parameters. Now we can estimate those parameters using either maximum likelihood estimation or maximum moment. I think I can explain this one later. And here we discuss maximum moment. So consider the case when omega has m independent parameter, and the basic idea is to compute m theoretical moment to appropriate m empirical moment to get the estimated m parameter. So example is first see Cochrane overflow. So actually you can ignore this part, and let's think about everything intuitively. So about AR1 procedure. Okay, so we can use the Cochrane overflow procedure, and we already learned how to calculate this and this. Okay. And about MA1 procedure, okay, suppose epsilon looks like this and E looks like this. And we know variance of epsilon looks like A squared, B squared, sigma E squared, and covariance between E epsilon T and T minus 1 looks like this. Okay. Note that we cannot separately identify all three parameters in the case. Okay. We have all three parameters means we need to estimate A, P, and the variance of Y squared, which is sigma E squared. Okay. We cannot separately identify all three parameters because A, B, sigma E squared has the same structure as A, sigma E, and B, sigma E squared, and 1. Right? So thus, with no loss in generality, what people usually do is they impose sigma E squared as 1. Okay? Then in this case, basically what we can think, basically since we are assuming that this part is 1, right? 1, so it means that variance of epsilon would be A squared plus B squared. And covariance between epsilon T and epsilon T minus is simply AB, right? We have two equations, two unknowns, basically we can solve it. So about the variance of sigma squared, so again, you can run the OLS regression, and from the OLS regression, you can collect your OLS errors. And you can simply calculate the variance of this error term, which should be equal to A squared, B squared. And on the other end, suppose you have an OLS estimate of those error terms, then you can simply calculate this one and this one. Okay, so you give the rec and multiply each other and get the average, then which will be the estimate of the coefficient, covariance. So which should be AB. And we have two equations and two unknowns, so we can solve this one. Okay? Solve this one for A and B. This kind of procedure is called the method of O. Okay, so about heteroscedasticity of the second way. Suppose our variance about observation at time t is proportional to one of our independent variable stk, right? And basically we can write down sigma t square as a sigma square and xtk square, right? Then what we can do is run a regression. So again, we do the OLS first. From OLS, we collect those error terms and we scale the error term and run regression with this one to this one. Okay. Given the model specification, we usually assume this is 0 and this is sigma square. Okay. And this kind of procedure is called method. Any question? And they're all straightforward, aren't they?
First and 2 colon sigma security.
Where?
Number 3.
Number 3, which one?
2 colon.
No, it is heteroscedasticity, second type of heteroscedasticity. So it is the, it starts from this. So heteroscedasticity 2, this one is basically this. Our heteroscedasticity, there is a heteroscedasticity 1 is we assume variance is all different, but we don't give any structure of this one. Second type of heteroscedasticity 2 is looks like this one. Okay, and we wanna estimate this one, which is okay, so intuitively, so as you can see, GLS, generalizable squarization, is not that difficult. Always you run OLS first, and from the errors of OLS, you correct the errors of OLS, and given by analyzing those errors from OLS, basically you find the parameters for GLS for the various covariance matrix. In the GLS, and once you know the omega, once you estimate omega from this OLS division, then you plug this omega into this one, okay? Into this one, okay? To calculate the estimate of GLS estimate of beta. once you estimate geoelectric beta, then variance covariance measure beta is this one. So you can calculate t value and p value and everything. Yeah, I think this is it for today. No question. Okay, then see you next week.